Good morning or good afternoon, everyone, depending on where you're joining us today. So welcome to UNIDIR's Technology Breakfast on navigating the technological landscape of microchips. And today we will delve into the latest developments in microchip technology and how they can enable innovations such as artificial intelligence. My name is Wenqing, and I work as an associate researcher for UNIDIR's Security and Technology Program. Today, I'm deeply honored to be joined by Suchi Srinivasan, Managing Director and Partner from Boston Consulting Group, where her work focuses on growth strategy and commercial operations across infrastructure, semiconductor, and application software players. Suchi, it's a great pleasure to have you here.
I'm so pleased to be joining you all and having this discussion with a focus on AI chips. Thank you for having me here.
Thank you so much, Suchi. So next slide, please. Today's event marks the second session of UNIDIR's Technology and Breakfast series. Maybe some of you actually attended the first session in May. And this series aims at exploring key technology domains that are enabling or driving further development in information and communications technologies, as well as artificial intelligence. And the series builds upon the research insights from our recent Compendium, which you can access through the link or the QR code on your screen. I will also pass the link in the chat for your ease of reference. So the publication identifies and analyzes the most salient advancements in enabling technologies and their impact on international security, encompassing 4 distinct technology categories, including, as you could see on the screen, advanced materials, parts and components, processing and computing, as well as connectivity infrastructure. And today's event with a focus on microchips. And this topic actually falls under the parts and components category of the Compendium. And we will begin today's briefing with an introductory overview of microchips and their latest development as presented in the UNIDIR Compendium. Following this, we will then hear from Suchi, who will shed light on how microchip technology is driving innovations in the field of AI. And just a few housekeeping remarks before we delve into the substance. So there will be a dedicated Q&A session at the end, but you may pose your questions via the Q&A function on WebEx and at any time during the event. So please note that the event is being recorded and it will be available on UNIDIR's YouTube channel afterwards. However, we will not record the Q&A session at the end just to encourage an open and frank conversation. So next slide, please. Thank you so much. Well, I guess first, it's very important to address this fundamental question. What is a microchip? Even though we know it is all around us, we might talk about it all the time. But we might not, entirely familiar with the concept. So a microchip or a chip, also known as an integrated circuit, is a compact assembly of miniaturized electronic components, including, among other things, transistors, diodes, and resistors, all on a very small flat piece of semiconductor material, usually a silicon wafer. And there are many different types of microchips that support the functioning of our digital life. Logic chips are the brains of computers, so to speak, and they do all the heavy lifting in a way. For instance, they can process the data and execute instructions to perform various tasks. Central processing units, or CPUs, are the most common type of logic chips, so I'm sure many of you must have heard about it. They are able to handle all computing tasks required for operating systems and applications. Some logic chips are designed for more specific functions and support high-performance computing. For instance, graphics processing units, or GPUs, were initially created to optimize visual displays, but now we are also more often seeing their applications in AI. And I'm sure Suchi will delve into this topic more in depth later on. In addition, neural processing units, or NPUs, are specifically designed for deep learning and machine learning applications. Memory chips, on the other hand, store information in electronic devices, with data storage being either volatile or non-volatile. Volatile memory chips, such as dynamic random access memory or DRAM, provide temporary data storage for running applications and require a constant power supply to retain the data. Non-volatile memory chips, such as non-flash, they can save data even after the device is switched off. And other chips may integrate the functions of both logic and memory chips, along with additional capabilities. For instance, application-specific integrated circuits are customized for specific applications rather than general purpose use, which can ensure high efficiency and performance. System on a chip is a new chip structure that integrates different components of a computer system, such as CPUs and memory, all together onto a single chip. It is commonly used in smartphones and Internet of Things applications. Next slide, please. Thank you. So over the past decades, as we have witnessed, our electronic devices have evolved significantly. They become increasingly compact, powerful, and energy efficient. And the computing capabilities of our digital devices have grown exponentially. And this development is largely owing to advancement in microchips and in particular, the semiconductor technology used for microchip manufacturing. Currently, silicon is the most commonly used semiconductor material, but other materials such as gallium arsenide and germanium are also used in specialized applications. On microchips, transistors play a very crucial role as miniature electrical switches capable of turning the electric current on or off. And this capability forms the very foundation of modern electronics. Essentially, the more transistors there are on a single chip, the more powerful the computing capability will be. So the process node of the transistors is another very critical indicator in semiconductor technology, as smaller process nodes will allow for more transistors to be packed onto a single chip. And this often improves the performance and energy efficiency of microchips. Semiconductor node size has reduced dramatically over the past decades. Initially, the measurement of process nodes was actually in micrometers, and now we are talking about the most current and cutting edge level of 3 nanometer technology. So it's a jump from micrometer to nanometer scale. The production of the next generation 2 nanometer microchips is expected to start in 2025, which is projected to achieve processing speed that are even 10 to 15% higher than the current 3 nanometer technology. And the driving force behind the semiconductor evolution is what has become known as Moore's Law. Gordon Moore, a co-founder of Intel, observed in 1965 that the number of transistors on a microchip has, historically tended to double approximately every 2 years. So what this means essentially is that there will be more transistors to be embedded on a single chip. So this in turn can lead to enhanced performance and also higher energy efficiency. While Moore's Law has largely held true into the 21st century, current silicon-based semiconductor technology is gradually approaching its physical limits. So the industry is currently looking at alternative materials and approaches to sustain the growth and transformation of microchip technology. Next slide. Thank you. And in addition to advancements we are seeing in semiconductor technology, microchip innovation is equally driven by improvement in many different domains, such as chip design, manufacturing process, and packaging techniques. In recent years, innovation in chip design methods have led to enhanced microchip performance. For instance, the multi-die and or chiplet-based systems, and they are very different from the traditional monolithic chips, as they consist of a collection of specialized chips, such as CPUs and memory chips, all together, and which are linked to create a very complex and integrated package. And this architecture can support high-performance computing and reduce waste in the chip manufacturing process. In addition, leading companies have designed custom microchips to optimize performance for specific applications and workloads. It's an approach known as custom silicon. These specialized microchips enable advanced applications like 5G and artificial intelligence. For example, 5G necessitates the development of advanced microchips that can meet the technology's high speed and low latency requirements. Secondly, in microchip manufacturing, extreme ultraviolet or EUV lithography technology is very crucial for producing the world's most advanced microchips. It is essentially a process of using light to print nanoscale patterns onto photosensitive silicon wafers. And this technology facilitates the creation of ultra-small and highly precise microchip components. A more complex method, known as high numerical aperture EUV lithography, is now being developed to achieve the next generation 2-nanometer technology. Lastly, advanced packaging methods also help enhance microchip performance and energy efficiency. For instance, through the three-dimensional packaging that stacks multiple chips vertically, and this vertical configuration improves communication between the individual chips, leading to faster signal transmission and reduced power consumption. Next slide, please. So as we just briefly went through the latest innovations in the field, I'm sure the topic might be very technical for many of you, and you may be wondering now, what are the international security implications of all these developments? So advancement microchip technology will continue to shape the technological landscape in the coming years, which carries actually quite significant implications for international security. Electronic devices and systems are pervasive in modern warfare, powering a range of different military equipment from drones and missiles to armored vehicles. Enhanced microchip performance thus offers significant benefits for military operations. These include, for instance, increasing the precision and effectiveness of advanced weaponry, boosting intelligence, surveillance, and reconnaissance or ISR capabilities, improving military communications, and facilitating the adoption of AI and autonomy within military systems. And however, it's also important to highlight several security challenges inherent in microchip technology and the industry as a whole. The microchip supply chain is a highly global, specialized, and complex network, from chip design and manufacturing to assembly, test, and packaging. And currently, no single company or country is capable of performing all the different processes internally. In addition, the most advanced technologies and manufacturing capabilities are often concentrated in specific regions. For instance, the Dutch company ASML is the only company currently capable of producing the EUV lithography machines that we just mentioned briefly before, that are used to manufacture the world's most advanced microchips. And the highly specialized supply chain is very susceptible to disruptions, which can negatively impact the availability of microchips. This issue became very real during the COVID-19 pandemic when the world witnessed a major microchip shortage that led to disruptions across different industries and also resulted in significant price increases. The shortage was caused by a combination of factors, including COVID restrictions and severe weather events, impacting chip manufacturing capabilities in certain regions of the world, and an elevated demand as people shifted to working from home. Second, microchips inherently possess a dual-use nature. They can be found both in a microwave at your home and also a guided missile in the battlefield. And this creates a risk of potential misuse as microchips designed for civilian applications such as smartphones and laptops may fall outside as per control regulations, but can nonetheless be exploited for military systems or repurposed for military applications. Lastly, cybersecurity risks are unfortunately not confined to software only, and they exist equally in hardware, a problem commonly known as hardware trojans. Due to the complexity of microchip architecture, detecting hardware manipulations in microchips remain quite challenging. The physical modification to microchips can effectively be concealed among the large number of valid components on the microchips, and they may stay undetected for an extended period. And this creates a window of vulnerability and put the broader digital systems at risk. To address this issue, ongoing efforts are now focused on developing effective detection methods. So these are just some general observations from the UNIDIR research on microchips. I will now turn to Suchi, who will provide some more insights into the development of microchips for AI applications. Suchi, the floor is yours. I will share the slide.
Thank you, Wenting. Good morning, everybody. Hello from Seattle, where the sun is still just about to rise, and it's a pleasure to be here with all of you. I'm picking up on Wenting's introduction to the field of microchips to get into AI microchips, which is a specialized set of microchips that are specifically, getting developed to handle sort of the demands of AI. So the purpose of our conversation today, in the next 15 minutes, what I'll attempt to do here is try to explain a little bit about what makes them different than the rest of the microchip land. What are some emerging developments? How are they growing? What are the nature of the usage from AI that requires the speciality? And then let's also learn a little bit about what those AI applications look like in different verticals, right? Like what's the AI getting used for? And that then will naturally lead us into some of sort of the complications, building on Wenting's point around supply chain, but also, a few other nuances around AI microchips. I'm sure you all are following the intense demand for these. So just trying to unpack that a little bit better, and then concluding therefore with, if you will, some of those implications for, global security and international politics. Let's go to the next page. So if you think about what Wenting just talked about, all the different functions on the chip, what's unique about AI workloads is, the number of AI workloads tend to be very strenuous and demanding in the number of operations that they need to do sort of on a per second basis, right? And that essentially boils down to mathematical operations. And so historically, CPUs, which were the most commonly used sort of chips that are powering all of our computers, were designed for a steady throughput of these operations, because things like Word and PowerPoint are not essentially very mathematically intensive. And so the desire was there to keep these chips flexible, to be able to handle a number of different operations, not just the math ones. And at the same time, the flexibility is what keeps the cost manageable, because you can use the chip for a number of different purposes. And performance, as long as it was sort of able to handle average performance, consumers were pretty happy. So you can kind of think about it as the pictures on the bottom of the page here. There's a train, it's running on time. The tracks are able to handle a certain number of trains per day, right? That's the way to think about it. GPUs were originally actually designed to handle graphics processing when you think about video games, which are definitely a little bit more math intensive than the average CPU operations. And therefore, they weren't originally designed for AI. They were just designed for graphics. And you can think about that as sort of the multi-lane highway, right? That's the load that graphics processing is putting in. It so happens that as AI came along with its intense demand for massive amount of math operations, the first chip that was easily available that could actually start to handle AI operations more efficiently and more cost effectively than CPUs were GPUs. And that's why, you hear GPUs a lot in the news today. But there are further kinds of specialized AI chips, and that picture is a funny picture because I couldn't think of how else to show it, but you almost want to imagine a three-dimensional space where you're now stuffing those cars into vertical lanes in addition to horizontal ones. But you get the point. An extreme density in a very custom designed chip that allows the maximum number of sort of operations, right? That's the logic over here, is you want to be able to do this as energy efficient with greater accuracy, in a very, very hyper customized way, because the load is so strenuous. Let's go to the next page. And why is there such a focus on designing these chips, right? Like, why can't we just use the GPUs and CPUs, and it's fine if they aren't efficient, let's just throw hundreds more or thousands more and just use them. The reason for that is the amount of data that's coming through these systems that AI systems are expected to process is insane, is absolutely insane. It is growing to numbers that are just not fathomable or even humanly imaginable. We can't grasp our hands around what that means. So all of the file servers in the world are not going to have enough capacity to transact all of the IoT data, as machines are coming online. For example, cars are coming online, factories and manufacturing places are coming online, smart cities are coming online. This amount of data is just humanly unimaginable. So you've got to get very, very, very efficient in processing it. The second point is the energy consumption, right? I'm sure you're already hearing about the fact that new data center construction is becoming more and more difficult because you need sort of this reliable supply of energy. And AI is very, very, very power hungry. And so, to be able to specifically custom design AI chips that can minimize that energy consumption is actually a very big deal and matters a great deal for the planet. And last but not the least, the latency. Can't afford to have these things be slow. I'm sure all of you have used ChatGPT, and even microseconds or milliseconds of delays is very discernible. And folks, especially in many enterprise and business situations, don't have a lot of tolerance for all of that. So that's why we're having almost sort of this subfield of custom AI microchip design. Let's go to the next page. So this is a lot of acronyms and a lot of terms out here, so I won't bleed the page here. But just to give you an idea, Wenting already talked about the CPUs, which were the general purpose ones. I just talked about the GPUs, which originally started off, NVIDIA, of course, has been the bellwether here with the GPU line, with their graphics units that powered all the video game players, and now have really morphed into the main supplier for AI chips. But there are two other kinds as well, what we call FPGAs, which are essentially, the way you want to think about it is, these are chips that offer a small number of customization. So they're not as general purpose as GPUs. You can't just plug and play them. But let's say you had a medical application or you had a financial application that had a certain type of application requirements. You could customize this within a certain set of factors to be able to get the most optimal performance. So it's a more specialized, the degree of specialization is increasing as we go down. And ASICs are the extreme example of completely custom-built chips, right? So they're designed for one particular application, hence the name, application-specific integrated circuits. But as you can imagine, there are going to be performance and other types of efficiencies that will come out as a result of that extreme level of specialization. So the more specialization, potentially the better performance, but of course you have to balance that with cost, which leads me to the next page. Therefore, they're not all created equal, right? There are trade-offs, right? And this is really, you know, as enterprises or governments, public sector are looking at which to employ, you know, as you can see, if, you know, a fully shaded green here means sort of the best in class. And so you can see that performance rises all the way through with the ASIC sort of performing the best. And by definition, that's because it's hyper specialized to what the need is. But at the same time, if you go by definition, the third row, the flexibility and the general usage, for sure, the ASIC does not offer flexibility because it's custom designed. The implication for this is, you know, the cost for manufacturing, the cost for usage. Obviously, as you can imagine, it's more expensive to create an ASIC. It's more expensive to manufacture it. It's more expensive to buy it. And so you really want to have, as a customer, you want to be able to have enough scale in the usage, and you want to have enough return in terms of value creation to be able to actually think about an ASIC. Otherwise, you might be picking one of the other options. And GPUs are rapidly emerging as sort of a, you know, very general purpose choice, which actually leads me to the next point, because people are trying to predict, you know, winners and losers. So if you go to the next page, it's not simple for that reason, right? It's not, I know there's a lot of hype right now. You know, NVIDIA is sort of the player that seems to be everybody's darling. But the truth is that there are pros and cons of each of these architectures, and it's not a one size fits all. And so whoever is deploying these is going to look at what the needs are, right? How much do you expect the usage to never change in the lifetime of the chip and is going to be static, versus how much you think you might want to redirect tomorrow because you're a data center operator, you want to be able to support different types of applications. You know, where is the most sort of bang for your buck? Where is the ROI? Which architecture can scale? These are, you know, one word about training and inference. I'm sure these terms have crossed everyone's reading list quite a bit. Training is the process of training models like GPT-4 to be able to actually learn. Think of it like going to school or grad school to be able to actually learn content and therefore be able to answer sort of very specialized questions. Training is extremely compute intensive. And today GPUs are the preferred option to be able to do training. You do see a couple of examples. You do see many sovereign governments wanting to train, you know, sort of models, whether it's in their local language or whether it's based on sort of their local information and, you know, policies, procedures. You also see training in domains, you know, a model for finance or a model for manufacturing. Inference is once the model has gone to school, so to say, or has been trained, you know, simply being able to borrow a book from the library, read it, and be able to answer the question, right? Again, I'm trying to give some simple examples here. And that is actually, you know, again, lots of GPUs and even some CPUs getting used over there, but ASICs are by far the most efficient. So you can see the logos out there. There's a lot of players. And if you go to the next page, this isn't the complete list of players. I'm not going to go through every line out here, but even though it seems like the hardware is only one piece of the system and you have a lot of software on top of it, disproportionately, the hardware is almost like it's the gating function, it's the foundation, it's the core infrastructure. So right now, it's disproportionately important. The application ecosystem isn't mature, and it's the infrastructure build out that is happening all over the world. And so while you do have GPUs taking up the lion's share at 70% of market share with all of those familiar logos, I want you to note two things out here. One is that folks like Google, Amazon, Microsoft, Meta, the big hyperscalers are deeply investing in their own hardware versions because no one wants to have a single point of failure and dependence. So the market doesn't like to have one single player that's sort of concentrating everything. So there's a lot of money and investment that's flowing into that. Secondly, the logos are very small at the very bottom, but there is actually a very healthy, thriving hardware ecosystem, probably the first time in several decades that it's been this robust, and lots of venture capital and investment money capital that's flowing into this place because there's a desire to be extremely innovative to address the new problems being posed by AI workloads. Okay, so it's a very robust ecosystem. Let's shift on the application side and go to the next page. There are two ways to think about the demand for AI. AI applications reside in a number of places, right? We talked about the first column, which is the large language models. The best example for that is ChatGPT. Globally, universally, I think everybody's used that, and there are many variations of it regionally across the globe. That's an example of it. It's getting a lot of commercial applications, everything from customer service, operations, and so on and so forth. We do have data centers, such as the ones that do run inside Google, Microsoft, Amazon, as well as several enterprise data centers that have many AI applications. Edge and embedded, the way to think about it is even your mobile phones that you're holding in your hands these days, or the AI PCs that are beginning to come out from all the big names like HP, Dell, and Lenovo, are examples of edge, which means by definition, it sits with you, the end user, and it's also running AI. And then we have a few other specialized AI applications. So these are all the places where AI runs. The short version is it's rapidly becoming everywhere, in the cloud, on your device, and inside the enterprise. The other piece is what types of applications are we talking about? So if we go to the next page, it's everywhere again, and this is not an exhaustive list. So if you've been following all the talk about autonomous driving, to whatever degree it is, it doesn't need to be even fully autonomous, level 4 or level 5, but even the levels 1s, 2, and 3s that we have today, all of that is enabled by AI chips to be able to sense, look at the data that's coming in, make decisions, stopping the car, moving the car, etc. Healthcare has benefited hugely from AI. You've probably seen these announcements from everybody like, a number of the big pharma giants who are cutting down R&D time to come up with new drugs, shortened timelines for clinical trials because they're able to take in the data, read it much more easily, come up with conclusions. So lots of applications in healthcare. Manufacturing, as the workforce is aging, being able to use AI to teach essentially new, joiners into the industry, a technician co-pilot, almost, if you will, to be able to take in all of the manuals, data, So there's lots of applications in manufacturing, and of course in finance as well. Whether it's investment banking, research, analysis. You can imagine a ChatGPT-like application that allows you to research and make sense to be able to optimize investments, cryptocurrency, fraud detection, payments. There's a very long list of use cases, and many of them are in the news. I'll go to the next page for one example from also sort of smart cities and smart government. The public sector is not isolated and is equally benefiting, whether it's education, whether it's governments, whether it's smart cities. There is an opportunity here to use AI to be able to really optimize a lot of these things. And what we see is we've got numerous examples globally, whether it's the city of Dublin, whether it's California beginning to roll out things. So there's a lot of new use cases that are being used and deployed in AI. So the public sector is equally a user of these AI chips, right? That's basically what I want to point out here. Therefore, the last part of our discussion here is how do we navigate? What are the the forces that are affecting the AI chip industry? What do you need to be aware of so that you can then be mindful as you think about the security and other implications? And so there are two types of forces as we think about it, right? The first one is cyclical, which means that these are intrinsic. They've been around sort of forever. And if we go to the next page for a minute, this is what I mean. Again, I'm not going to read every line on this, but an example of macroeconomics, of course, is our inflation and deflation cycles. This happens regularly, once every so often. And semiconductor has actually always been very famous for being a cyclical industry, and that's just part of almost normal business. Competitiveness, though, has picked up a lot recently, where there was a lot of consolidation in the industry, and the reason for that is the R&D is becoming more expensive, more competitive. The stakes are getting higher. And there's an increased cost of doing business, as we'll talk about it here, to be able to take care of some of the supply chain risks and things like that. So it's becoming more expensive and more competitive. I know there's a lot of talk, I'm sure, during your day today about various types of geopolitical conflicts, but the geopolitical landscape has just become more complex to navigate, right? And so raw materials set in some part of the world, factories and manufacturing facilities are built in another part of the world. Things have to be delivered. There are disruptions here, both geopolitical in nature as well as disasters, which of course can never be predicted. And we have different versions of it. I think the world is still actually recovering from a reconfiguration post COVID-19. And so these things really are what we bucket as cyclical factors that are affecting the supply chain. If we go back one page, I want to go back to the previous page. The one before this, yes. Thank you. And all of the headlines that you probably saw in the last couple of years, car shortages because semiconductor chips were not available. That's an example of some of these cyclical factors, which always used to exist, but we feel it very acutely now because it's in our everyday lives, right? We're all using these devices. I'll end with talking about the structural shifts, which are newer, right? They didn't used to exist as much before, but now they're becoming more important. And I think, it's important for all of us to educate ourselves about it and therefore be aware. One is sort of the chip pervasiveness across industries. An example of that would be, the average car that's getting produced during this decade is having upwards of 40% of its bill of materials is semiconductors. That's unimaginable. When Ford Motor Company started with the Model T, there was no semiconductor in there at all. And it stayed actually fairly static even through the 1970s and the 80s. There was just very, very limited semiconductors. We're having an explosion of usage as every industry transforms into a tech-first industry. Auto is a great example of that. The next point is the global capacity, right? As there are regulatory, I think there's a couple of pages here we can just, go forward and show. One more. Yeah. No, that's okay. As there are more sort of, and Wenting also referred to this, right? There is concentration in the supply chain, which produces risk. There's also regulatory hurdles to being able to, for example, set up new manufacturing facilities and things like that. And so chip manufacturers and chip designers have to navigate all of this to be able to actually produce, the end outcome. And that's a non-significant amount of risk, right? And one more, if you go to the next page and the last page, is the industry is right now, not very efficient in its usage of water, management of waste output. We talked already about the energy consumption, also in the manufacturing of these AI chips, and the carbon emissions, right? And they are aware of it. A greater number of them are beginning to print out their sustainability reports and declare it and making efforts, but in comparison to other industries, it's actually still fairly nascent. And again, this matters because there are increasing number of nations in the world that are both mandating disclosure, which of course leads to public information about all of this, as well as, they have standards in order to be able to set up facilities or be able to use parts of their country. So it's a very complex landscape to navigate, and this is increasing day by day rather than reducing. So I'll leave you all with the thoughts that AI is simultaneously becoming the most important piece of infrastructure build out in our generation to be able to enable dramatically new ways of living and working globally. No country is immune. And at the same time, the infrastructure upon which it is running, dare I say, is a bit fragile and is very resource intensive, and is very concentrated around the world. Therein lies the primary challenge for global security. I'll take questions.
Yeah.
Hope that gave you a bit of a look into the world.
Yeah, thank you so much, Suchi, for the fascinating presentation. It's really interesting for me to learn about, how microchip technology is facilitating concretely the applications of AI, and you also highlighted several, important trends for us to, look out for in the future AI chip industry. So thank you so much for that.